Assalamu alaikum students, welcome to lecture number 13 of this fluid mechanics 2 course, and we were discussing the converging and diverging duct flows, and we derived a relation in which we saw the change in velocity and the change in area. What were the effects on the subsonic and supersonic flow for a diverging duct and for a converging duct, and similarly we also saw the effect of density, that how it increases in the direction of area in the subsonic flow and how it behaves otherwise in the supersonic flow. So today we also need to derive some values for other state functions. For example, the pressure, temperature and density. We need to have equations of these state functions with relation to the Mach number, that how will they behave when they pass through a compressible effect like the converging or the diverging or the converging duct. So what will be the effect on these properties? So that's what we are going to do today. We are going to derive some relations and see their effect on the Mach number and how they change. So this is also another geometry of ducts that is used quite abundantly in turbojet engines, and in this case we were talking about the diverging ducts and the converging ducts separately, but here you can see that the converging and diverging ducts are combined. So this is called a converging diverging duct, and here it is called a diverging converging duct. So these two type of ducts is also used. So, just to summarize this paragraph, it is very important. That's why I pasted the whole paragraph here. To summarize it, we are now interested in defining different properties for our converging diverging duct. And let's say if this is our converging diverging duct, and we are interested in finding pressure, temperature, density inside this converging diverging duct, because inside there are compressible effects. There are compressible effects, and we are dealing with compressible flows now. So to see the properties like pressure, temperature and density of a compressible flow, so it is an ideal way to visualize it is in a converging diverging duct. So just like we did in the Bernoulli's equation case, that we would take 2 points, point 1, point 2, or section 1 or section 2, and apply Bernoulli equation on section 1, apply Bernoulli equation on section 2, then cancel out some terms and derive the equation for your velocity or pressure or elevation or whatever that was required to be calculated. So here in this scenario we also need a reference point, a starting point that will be used to compare the pressure, temperature and density inside the nozzle. So the reference point in this case will be our outside atmosphere, our atmosphere from where this nozzle is sucking in the air. So the reference point will be the atmosphere, and that reference point, that atmosphere, will be referred to as the stagnation point in this literature. Stagnation point. So for compressible flows and for the measurement of pressure, temperature and density inside the nozzle, the reference point will be the atmosphere, and we will take the atmospheric pressure P0, the atmospheric temperature T0, and the density of the air at a certain atmospheric conditions, and find the pressure inside the nozzle, temperature inside the nozzle and density of fluid inside the nozzles. Also in relation to the Mach number, that will tell us that what will happen if our flow is subsonic and that flow is entering into the nozzle. So what will be the effect of pressure, temperature and density then, and what is supersonic, then what will be the effect of these state functions. So as I said earlier, we needed a reference point, and the reference point will be our atmosphere, and that atmosphere in this literature is referred to as the stagnation point. Why the stagnation point? Stagnation point, if you remember, when we were studying the Venturi meter, and Venturi meter was used to calculate the velocity of the aircrafts, and it was placed upstream in a flow, and whenever a flow will come to this point, it will be brought to rest. So that point was also known as the stagnation point, if you remember, and that pressure was known as the stagnation pressure. So when a fluid, when a certain converging diverging nozzle like this is sucking in the air from the atmosphere, so the conditions right here, for example, if I redraw this converging diverging nozzle, the conditions inside the nozzle are not static as compared to the outside the atmosphere, which are quite static. You can assume the pressure to be stagnation pressure, you can assume the pressure to be temperature to be stagnation temperature, and the density to be the stagnation density of the fluid at these pressure and temperatures. So in relation to this scenario, inside the nozzle, the outside atmosphere is pretty much static, and that's why it is known as the stagnation point, and that's why we will refer to these pressures as stagnation pressure, and temperature and stagnation density. So whenever you come across the word stagnation pressure, temperature, or the stagnation properties, so they will be referring to the atmospheric properties. And just for solving different problems and example, we will use the tables of standard atmosphere we will use our tables of standard atmosphere to see the values of pressure, temperature, and density. So these tables will be used, the tables of standard atmosphere, at the end of your Munson book, and you are already familiar with the term the standard atmospheric conditions. So we will use standard atmospheric conditions for the stagnation, pressure, temperatures, and densities whenever we encounter them in a problem or an example. So now this was just to summarize what was written, and you can also read that, and I urge you to do that, because you will get the sense of what I am talking about and how these stagnation concepts were used previously in the fluid mechanics 1 course when we were talking about the Venturi meters and the RFSs. So it's a good read, please give it a read. So now what we are concerned about, what is our main concern, is to derive some equations that will give us the pressure inside the nozzle, the temperature inside the nozzle, and the density inside the nozzle of the fluid. So just to see, what we will assume is that in section 11.1 we demonstrated that for an isentropic flow of an ideal gas we derived these equations. So this will be the pressure and density inside the nozzle, and this will be the pressure and density at the atmospheric condition, or the stagnation pressure and density. So one is this assumption that our flow is isentropic. By isentropic we mean that it is adiabatic, and it is frictionless. So by assuming these two, we can actually say that our flow is isentropic, and we will use all our isentropic flow equations to derive the terms that are required. So the next is in use will be the streamwise equation of motion. That was the Bernoulli equation, in which we eliminated the rho dz term, because we said that the elevation terms are not that dominant in this study, so we will neglect that term, and after neglecting that term we were left with these terms only. So by combining these two equations, this equation and this equation, we will get this term right here, and then again we will use this term in combination with some other equations. You can see the derivation of this equation and the equations that we are going to use in the next slide. in your Munson book. I'm not going to do that here, but I'm going to just write the final equations that we got after the derivations. So this is the equations that we are going to use to derive our equations for our stagnation temperature and temperature inside the nozzle, stagnation pressure and pressure inside the nozzle, and the stagnation density and density inside the nozzle. So this is the temperature. If we want to find the temperature inside the nozzle or the temperature of a compressible flow inside the converging divergent nozzle, we can use this equation. This is the temperature inside the nozzle, this is the temperature, the stagnation temperature, and you now know what is the stagnation temperature. This equation is given in relation to the Mach number. Similarly, this is another equation in which the pressure inside the nozzle and the stagnation pressure in outside is given in relation to the Mach number, and similarly for our density inside the nozzle and the stagnation density of the outer atmosphere in relation to the Mach number is given with the help of these three equations. Their derivation is given in the Munson book and they are all derived from this equation, and you can go through it by yourself. So if we use the standard atmosphere and we use air as our standard gas, so we can actually put some values. We have a specific heat capacity ratio K value for air. We will put that here. We know the standard atmosphere temperature T naught, standard pressure P naught, and standard density rho naught for air. We can put that here, and then we can substitute different Mach values. We can substitute different Mach values both for the subsonic regime and the supersonic regimes, and plot these graphs that you see right here by finding the value of T. If we suppose take some values from the table and put some values of Mach number from subsonic to super and hypersonic regimes, so we can actually find the temperature, pressure, and density values for air inside a converging diverging nozzle. And these are the graphs that we can also plot if we have all the values. These are for T over T naught, P over P naught, and rho over rho naught. So just as we said, for isentropic flows, the temperature, pressure, and density ratios are a function of Mach number, as you can see from the graph and from the equations as well, that the temperature, pressure, and densities, they are all a function of a Mach number in case of an isentropic flow. And this is what we want. We want to see the effect of temperature, pressure, and density with relation to the Mach number, because the Mach number tells us about the compressibility of fluid. This is what we already discussed. So now let's talk about a condition that is called choke flow. And what is choke flow? We will use a converging diverging duct to explain this phenomenon. And let's say that this is the outer atmosphere, the stagnation reference point, which is at rest. This is the upstream of this nozzle, this is the downstream of this duct. So the fluid is going in this direction, and what it does that the converging portion, that is the throat, is actually accelerating the flow, given that the flow is subsonic. So the flow is subsonic, it is passing through this converging diverging duct. In the upstream, the flow is being accelerated due to the presence of this converging throat. So in the downstream, what if we start decreasing the pressure? If we start decreasing the pressure, then what will happen? The velocity will start to increase more and more. So the velocity will increase, and so much so that by decreasing the pressure further, that the velocity will increase so much that a Mach number of 1 will be achieved. So when this condition is achieved, and by decreasing the pressure further after achieving Mach number is equal to 1, there will be no change in the Mach number, which means that the velocity of the upstream fluid will not increase further for a given pressure at the upstream. So what will further the consequences of this flow? The mass flow rate will not change. That let's say the by increasing the velocity, the mass flow rate was also increasing. So after attaining a Mach number of 1, the mass flow rate will have a certain value, let's say x, and by further decreasing the pressure downstream, the Mach number, and that is 1, and the mass flow rate, that was x at the time of Mach number 1, it will remain the same. So the Mach number and the mass flow rate at a certain amount of pressure that was achieved after decreasing the pressure downstream will remain the same. So the Mach number and the mass flow rate will not change in a choked flow. So this is called the choking condition, in which the Mach number cannot be further increased by further decreasing the pressure downstream. That was achieved in the first place by decreasing the pressure downstream, having a constant upstream pressure. So the only condition in which we can break free from this choke flow is to increase the pressure here in the upstream. Increase the pressure here at the upstream. So then the mass flow rate will change, the Mach number will change, and then the nozzle, the converging diverging nozzle, will get out of this choking condition. So this is what the choking flow is, and this is the phenomena that is sometimes desirable if you want to keep the mass flow rate constant. So it is better that your orifice or your valve or whatever it is should be choked, so that will give you a constant mass flow rate. So this is called choking, in which the fluid properties like the Mach number and the mass flow rate does not change by if we further decrease the pressure downstream. So there will be no effect at the throat region on the Mach number and on the mass flow rate of the flow, and it will remain the same, and this condition is called the choking flow. So since we have this term, this actually gives us another opportunity that if let's say that at a choking flow the Mach number, we'll write it, let's write it, if the Mach number is 1 at the throat in a choke flow, when we say that the Mach number is 1, so we can actually use the previous equations that we derived for the pressure, temperature and density, and then derive equation for the choking flow, in which we will use the subscript star, the superscript star for our temperature, P star for our pressure at the throat, T star as our temperature at the store, and rho star for our density at the throat. So now we have a very interesting scenario in which we can find these state properties at the throat of the nozzle. So as we already discussed, we have already used stagnation state, for which the Mach number will be 0 as a reference condition. It will prove helpful to us to use the state associated with Mach number 1. Now we will put Mach number 1 in the equations that we previously derived, and we will write them for the pressure, temperature and density equations for the choking condition, and the same entropy level as the flowing fluid as another reference condition we shall call the critical state. This state is also known as the critical state, and it will be denoted as the with a star. So the choking condition is also called the critical state, and if you are given a critical temperature, pressure and temperature, then that will be represented as P star, T star or rho star, and you should understand that as the choking flow properties. So this was again this will be our critical pressure ratio that will be derived by putting in the Mach number is equal to 1, because we are now dealing with the critical state pressure and the stagnation pressure. So this will be our one equation, and we put k is equal to 1.4, that is for air, that is the nominal value of specific heat ratio for air. So we can have this relation that P star over P naught, that is the stagnation pressure, is equal to 0.528. Similarly, we can have the relation, the similar relation for temperature by putting the Mach number A is equal to 1, and after putting K is equal to 1.4, we can have this relation T star over T naught is equal to 0.83. Similarly, we can also have a relation for rho star over rho, that is for density, and for K is equal to 1.4, and we will have a relation like this for density as well. So these are all for the choking flows, and as we said, the choking flow is for a condition in which the Mach number and the mass flow rate cannot be further increased by reducing further the pressure downstream. So this is the choking flow, and these are the equations that will help us to find the pressure at the throat, the temperature at the throat, and the density of fluid at the throat region. So this is how this phenomena is important. This graph is very helpful in determining the different flow properties. For example, the pressure over stagnation pressure, the temperature inside the nozzle over the temperature, stagnation temperature, and similarly the density over the stagnation density. And it also gives us helps us to find the area and the throat area. So the area of the nozzle and the throat area. So for an isentropic ideal gas with K is equal to 1.4, that is for air, we can have different, we can find these different properties. For example, let's say that I solve a problem and I get the rho or rho naught value as 0. Let's say 48, let's say. So I will leave that 0.048 here, right here. So it will lie somewhere 0.48 here. So this is my line for density or stagnation density. So this will be this is the point, and I will now mark this point on other lines as well, and this line is for pressure or stagnation pressure. So this will be my stagnation pressure or stagnation pressure value. I can also get on this left side of the vertical, and then for the correspondingly I will go up and mark this value for my T over T naught. So I will get a value of T over T naught, and similarly I can also identify my area over the throat area. So by getting one value T over T naught, and by having a certain value here, and knowing the stagnation temperature, that is our atmospheric temperature, we can find the temperature inside the nozzle. Similarly for P over P naught, if we read a value from the graph, we can actually put the stagnation pressure and find the pressure inside our throat. So this is a useful graph that was provided by Bruce A. Reichardt, and we can use this graph to derive these, to find these relations, or we can use the equations that we just saw in the previous slide. So both can be used, this graph can be used, and these equations can be used. And now in the coming examples, we will use both these equations and the graph to solve a certain condition that is for a converging flow, I guess. So let's do that. So now let's look at this example in which we are considering an isentropic flow in a converging duct, and this is the flow scenario in which a converging duct passes air steadily from standard atmosphere conditions to a receiver pipe as illustrated in the figure. So this is the figure in which the converging duct is passing air by the help of this receiving pipe from this converging duct. So the minimum throat flow cross-sectional area of the converging duct is 1 into 10⁻⁴ meter square. The receiver pressure, this is the receiver pipe, so the pressure at one condition is 80 kilopascals, and we have another condition, that is B, for which we will solve separately, that is 40 kilopascals. Now what we have to find, determine the mass flow rate through the duct and the sketch temperature entropy diagrams for situation A and B. So what we will do, we'll find the mass flow rate through the duct. So first what we will have to do, we need to have our equations. So the first equation will be our mass flow rate. So determine the mass flow rate through the duct. So what we will do, we will find the mass flow rate at the throat of this the converging duct. So it will give us the mass flow rate, and this will be the equation that will be used. That will be the with the help of density at the throat, area at the throat, and the velocity at the throat. The area at the throat is given, the cross-sectional area 1 into 10 to the power minus 4 meters square, it is given. What we need to find is the density at the throat and the velocity at the throat. So for density, we can use our isotropic flow equations, in which the density at the inside the nozzle with respect to the stagnation density was derived in relation to the Mach number. So we can use this equation, but in this equation we don't know the Mach number and we don't know our our throat density. So these are the two unknowns for which we cannot solve this equation. So moving further, what we have to do, the stagnation density for standard atmosphere is 1.23 kilogram per meter cube. That is the stagnation density that can be read from the table given at the end of your book, and the specific heat ratio is 1.4, that is this K. So K is also 1.4 for air. To determine the throat Mach number, we can use equation 11.59, that is equation 11.59, but here also the throat pressure is unknown, the Mach number is unknown, the stagnation pressure can be read from the table, the value of K can be put 1.4. So for that purpose, what we need to do, first we need to find the critical pressure, and the critical pressure was the one that was the pressure at the choking situation, in which the flow was choked. So we are talking about the throat right here. So what we need to identify is the throat pressure. What will be the pressure at the throat when this flow situation is choked, when it is choked. So for that purpose, we already have a formula, that is P star over P naught is equal to 0.528. So by putting the stagnation pressure as the atmospheric pressure, that is 101 kilopascal absolute pressure, we get our choking pressure, that is critical pressure is 53.3 kilopascals absolute pressure. So this is the pressure at which the nozzle will be choked. But as you know, we are solving for a condition in which the receiver pipe is having a pressure of 80 kilopascals. We got that the receiver pressure is 80 kilopascals. So the P star, the critical pressure, is less than the pressure of the receiver. So in this situation, if the pressure of the receiver is 80 kilopascal, we can say that the nozzle is not choked. The nozzle is not choked, and we can take the throat pressure equal to the pressure of the receiver pipe, because if I draw this here, just the converging portion right here, and I take these two sections, section 1 and section 2. So at section 1 I take the properties act as the stagnation properties, and at section 2 I will take the properties at my throat. So whatever be the pressure of the receiver pipe right here, if it is less than the critical pressure, then I will say that my throat pressure is equal to the pressure of the receiver pipe. So this is what we are going to do. We are going to put in this equation, the pressure, the throat pressure, as that of the receiver pressure, that is given as 80 kilopascals, and for that purpose we will now have this value. We can put our atmospheric pressure value. We will put K is equal to 1.4, that is for air, because we are dealing with air at standard atmospheric conditions. So K is 1.4. Then by solving this equation, we can find our Mach number. So after finding the Mach number, we can actually use the Mach number in this equation and find our density at the throat, and again further by using the speed of sound equation we can find our velocity at the throat, and with the help of these equation we can actually find the mass flow rate. So this is what we already said, that if the pressure of the receiver, that is this one, is greater than or equal to the critical pressure, that is the pressure at the choking condition. So if it is greater than or equal to the critical pressure, then we will say that the throat pressure is equal to the receiver pressure. But if the receiver pressure is less than the critical pressure, then we will say that the throat pressure will be equal to the critical pressure, because we covered in the choking flow that choking flow is a condition in which the mass flow rate in the Mach number does not change if further you decrease the pressure downstream. So if we take a pressure value that is less than the critical pressure value, then nothing will happen. It will not have any significant effects in the flow. The flow will remain choked, so we will take the throat pressure as our critical pressure. But since our throat pressure is greater than the critical pressure, so that's why we are taking our throat pressure as that of a receiver. So with P throat and P naught and K known, we can find the Mach number from this equation. So now for finding the velocity, that was in the equation m dot is equal to density at the throat, area at the throat, and the velocity at the throat. So to find the velocity we are going to use this equation, and this is the equation of speed of sound, that is c is equal to under root RTK that we derived, and we already know that Mach number is V over C. So here instead of C we are putting Mach number and velocity at the throat, so that we can get an equation in terms of velocity. So what we will do, we will put C is equal to V over the Mach number, and we will substitute it here. So V over the Mach number is equal to under root RTK, and V is equal to Mach number into RTK. So for that purpose we already know the Mach number from our pressure equation. We know the universal gas constant value for air that can be read from the table. We need to find the throat temperature, and the K is 1.4 that we already know. So there are still one unknown, that is the throat temperature. So we will use this equation to find the throat temperature, and we will take for that purpose, if the standard atmospheric temperature is 15 Kelvin, we will convert it into the absolute value. So for that purpose, first we will solve the pressure equation to find the Mach number, then we will find the density by putting in the Mach number inside the density equation to find the density at the throat. So by doing that, let's clear up some space first. So by doing that, what we can do, we can find our temperature at the throat by using this equation once you have got the Mach number. So by finding the temperature at the throat, we can use the equation, that is this equation, to find the velocity at the throat. So now we know our velocity at the throat, our density at the throat. The area was already given in the statement, so we can proceed and find our mass flow rate. So this was the mass flow rate when the receiver pressure was 80 kilopascals. Now we will have to take the condition, that is condition B, and find the pressure, take the receiver pressure as 40 kilopascals. And if you do that, this 40 kilopascals is less than the critical pressure. So what we will do, we will take our, in this scenario, if we take the receiver pressure as 40 kilopascals, which is less than the critical pressure, then in that case our nozzle will be choked, and at the throat the pressure will be equal to the critical pressure, that is our pressure at which the nozzle is choked. So we will take the critical pressure value, and at the critical pressure we know that the Mach number is 1. So we will input the Mach number in all the equations that we just saw, as 1 and find our throat density, temperature and velocity, and find the mass flow rate as the result of these equations. So this is what we are going to do. We are going to take the receiver pressure as 40 kilopascal, and since it is less than the critical pressure, we have that the throat pressure is equal to the critical pressure, which is 53.3 kilopascal absolute pressure. And if the nozzle is choked, the Mach number at the throat will be 1. The converging duct is choked in this condition because the receiver pressure is less than the critical pressure. So now we can use all these equations once again by putting in the Mach number as 1. The K value is 1.4. We can have our stagnation density. We can find the throat density, which will be this value. Similarly, by putting the stagnation temperature value K and Mach number as 1, we can find our throat temperature. And similarly, using the previous equation, that is V is equal to Mach number into under root R T K. We can use this equation to find the throat velocity under choking condition. So it will come out to be 310 meter per second. So by doing some conversions first, finally we can use our equation for our mass flow rate, and for that purpose it will come out to be 0.0242 kilogram per second. So from the values of throat temperature and throat pressure calculate above for the flow situation, and B, we can construct temperature interface diagrams shown in this diagram. I have not included the diagrams in this slide. You can actually go through this example in the book and see the diagrams, that how these diagrams were constructed by using the equations that we just saw. So in the comments, just read out the comments. These are the points that we covered, but let's revise them. Note that the flow from standard atmosphere to the receiver pressure, that is the P receiver, greater than or equal to the critical pressure is isentropic. We already established that whenever we are encountering compressible flow, we are going to take them as isentropic. When the receiver pressure is less than the critical pressure, that was in this situation that the receiver pressure was less than the critical pressure. In this situation, that is P, what is the flow like downstream from the exit of the converging duct? What will be the flow behavior? So they are talking about the flow behavior if the receiver pressure is less than the critical pressure. So from the experience, from the experimental observations and from experimental experience suggests that this flow, when the receiver pressure is less than the critical pressure for a certain flow situation, is three-dimensional. The flow will be three-dimensional and non-isentropic. It will be not isentropic. It will be non-isentropic and involves a drop in pressure from the throat pressure to the receiver pressure, or drop in temperature and an increase in entropy as indicated in figure 11.c, which is given in your book. You can go through that figure. So what they are saying is if the receiver pressure is less than the critical pressure, so the flow that will be in the downstream will be non-isentropic. It will be three-dimensional, and there will be a drop in pressure as well as with the increase in entropy will also occur. So this was your example, and in the next example, what they have done, they have used the graph. They have used the graph that we saw in the slide number 5, I guess. So they used that graph to solve the same example. So kindly go through the that example by yourself and use this graph, and you will also learn to use this graph by just doing that example. It is very simple. So kindly go through that example that is just next to this one, and use this graph that is I guess figure D.1 given at the end of your book. So go through that graph, solve that example with the help of this graph, so that you understand the usage of this graph. So see you in the next class.